Well, good morning. It's 11:33, I believe it was. We're supposed to be starting class at 11:30, so I'm 3 minutes late. Sorry about that. But right now I'm the only one in the room. It's supposed to be Math 237, linear algebra. Hopefully some folks will be coming in, but right now I'm all alone. So, where we were last time, we're trying to wrap up Chapter 1, Systems of Linear Equations, 1.3 Applications of Systems of Linear Equations, and we talked about polynomial curve fitting. Was the first application we discussed, and this is an example 2 at the top of page 26. Okay, find the polynomial that fits these 5 points. Okay, let me get my pen set up. Okay, -2, 3, -1, 5, 0, 1, 1, 4, and 2, 10. Okay. Those are 5 points, evenly spaced on the x coordinate, but certainly not on the y. But these are your 5 points. Find the polynomial that fits these points. Okay? Now, 5 points, you'll need a 4th degree polynomial, always one lower degree than the degree of than the number of points. Think of it this way. A single point is just represented by a single point. So that would be a constant, okay? 2 points define a line. So then you need one less degree, linear equation, degree 1. 3 points fit by a quadratic, degree 2. 4 points fit by a cubic, degree 3. 5 points fit by a 4th degree polynomial, and always 1 degree less than the number of points you have. Okay, so our polynomial function would then be a sub 0, okay, plus a1x plus a2x squared plus a3 x cubed plus a4x fourth. Okay, 5 parameters here. That's what we need to find. Those 5 a's, a0 through a4. There's 5 of them. Okay. Now, what are the values? We know that. All right, I think we got a student coming. Good to see.
See, I'm the only one in here.
So far, if you will, hit the second light, not the first one. Yeah. Okay. Now, I'm going to pause the recording for just a moment. All right. We had a student come in and we just had a little discussion. So, back now. Okay. What we're doing is polynomial curve fitting. These are applications of systems of linear equations. They gave us 5 points here and said find a polynomial that will match those 5 points. Well, the smallest polynomial that's guaranteed to fit all 5 of those points will be a 4th degree polynomial. It has 5 parameters in it. A0 doesn't have an x with it, but then a1x to the first, a2x to the second, a3x cubed, and a4x to the fourth. Okay, so what we do next is plug in the x's and get the y's. Okay, so when you plug in the first x, that'll be at a0 plus or minus 2A1 plus, and the x value is squared. That will be, wait, I'm sorry, we do the 2's all the time. All right, plus 4x squared. We're plugging in 2 everywhere we see an, or negative 2 everywhere we see an x. Okay, and that would be minus 8x cubed. Now, I'm sorry. Goodness gracious. Writing these things backwards. Okay. We're plugging in the value for x, and that leaves the a values. So that would be plus 4a1, a2. Because you see the x is the minus 2 squared is plus 4 times a2. X cubed, that's minus 2 cubed, is minus 8 a3 plus 16 a4. See what I've done there? Well, not yet. Equal 3. Okay? Plugging in the x's here, x be minus 2 plus 4 minus 8 plus 16. Square cube 4.2. And that gives us the coefficients for our parameters here. And when you plug in the 2, you should get a 3. A negative 2, you should get a 3. Because 2, 3 is the point. This is your y value. The x's are your x values. Okay? So you tell me what the next one would be. What's that? Yeah, plug in the x. Yeah. A 0, that just comes down. Negative a1. No. Plus a2, because you square negative 1. Right? Okay. Minus a3, because you cube minus 1 and you get minus 1. Okay? A4 equal. Go back. No. 5. Perfect. Next one. A0. Yeah. Because all the rest of them are zeros. In fact, you saw that, I don't know if you saw it, but that polynomial, when all the x's are 0, is just the number 1. Okay? So that one's a pretty easy one. So really what we could do, I'll show you this in a minute. Let's go on to the next one. Yeah. Plus a1. Equal what? 4. Yeah, got it. And to a1. 4a2. 8a3 plus. All right. Now, a couple of things. First, you can reduce everything if you put, A0 is equal to 1. So put that in everywhere. In other words, subtract it from that side. And now you're down to 4 by 4 rather than 5 by 5. And that's going to be a lot better. Okay. So if you could follow what we're doing there, your A0 is 1, so you're going to put that in and subtract. So basically, your matrix, I'm going to put it here, is going to be minus 2, 4, minus 8, 16, and when you subtract 1 from there, you get a 2. Right? You're subtracting the A1 from both sides. A0 from both sides. Okay. A0 is equal to 1. So put a 1 here. Minus is, plus is, minus is, plus is. That's those. Subtract the 1 from here, and you get a 2. Okay. So I'm going to be subtracting from each of those. Okay? So, the next one would be minus 1, 1, minus 1, 1, 4. Subtracting that from there, right? I'm not going to even write the next one then. I'm using that one. The next one would be 1, 1, 1, 1, 3. Right? And the last one would be 2, 4, 8, 16, 9. Right? Okay. Now, really what we would like most is to have a 1 in the upper left. Now, there's 3 ways you can get that really easily. First is just divide that first equation by minus 2, because everything's divisible by 2, right? But divide by minus 2, and that would give it 2. Or multiply the second by minus 2 and swap those two. Minus 1 and swap those two, and that would do. Or just move the third equation up to the first. That would work too. I don't care which one. Which would you like? We got to deal with that, divide out the 2's anyway, so why don't we just go on and do that? Okay, is that all right with you? Okay, so the next step will be row 1 divided by minus 2 is the new row 1. Okay, so that will now be 1 minus 2, 3 minus 4, 1. Agreed? And then I'll write down the rest of them. Minus 1, 1, minus 1, 1, 4, 1, 1, 1, 1, 3. And almost could do the other one, but that would leave you a fraction at the end, so let's leave it 2, 4, 8, 16, 9. Okay, I'm going to move that up a little bit. All right, what do you want to happen next? We want 0 below that leading 1. Okay, how do we make that a 0? Nice, right, add. Add row 2 to row 1, right? Yeah. Row 2 plus row 1. That should do it. All right. I don't know where to put this. I guess I'll put it here. Okay, so leave row 1 alone. 1 minus 2, 3 minus 4, 1. New row 2 would be 0. What's that?
No, the second one would be 1.
Minus 1. Right? Next? No? 2. Negative 3. 5. Okay. What you want to do next? Subtract row 1. Yeah. Okay. So let's do it. 0. No. This one minus that. 1 minus a minus 2 is? Minus a minus 2 is plus 2. 1 plus 2 is? 3. Okay? Got it? It's row 3 minus row 1. Got it? Okay. Yeah. Okay. This one would be? Minus 2. 5. And 2. Right? What next? Row 4 minus 2 row 1. That'll make that a 0, right? Okay. So that'll give us a yeah. 2 minus 2 is 0. Okay? That's why we did it.
So you're going from, say, 2 row 1.
Yeah. Row 4 minus row 1. Minus 2 row 1. So row 4, 2, minus 2 times that is 2 minus 2 is 0. 4 minus a minus, so that's 3, 4 plus 4, 8. Right? Because it's row 4 minus 2 row 1. It's an ugly one. See what we're doing? Okay. So that would be an 8, wouldn't it? This would be 8 minus 3. No, minus 6 is 2, right? 16 plus 8 is 24. And 9 minus 2 is 7. Got it? Okay.
You just try to get the lines together.
Yeah. What you wanted is 0. You wanted 1 here, 0 below. So what's the next thing you want? You want that to be a 1, but it's a minus 1. So how do you get that to be a minus 1? To be a positive 1. Not add. Multiply by minus 1. Or divide by minus 1. Either one of them. So basically, we're just going to change the sign of that, right? Multiply by minus 1. So let me just do it in place because I don't have to write it again. Plus, minus, plus, minus. That work? Okay. Now what do we want to happen next? Now at this point, or at some point here, you have to decide, are we doing Gauss-Jordan elimination or just Gauss elimination? Gauss elimination, we're going to have to I want to say backfill, that's not as, what do you call it? Brain's going there. Reverse. Oh, there's a term for it. You go back substitution. Back substitution. Right. But if you do Gauss-Jordan, which is only a little bit more involved, then you just wind up with your answers. So which you want to do? Gauss elimination or Gauss-Jordan elimination? With Gauss elimination, we just get zeros below. With Gauss-Jordan, we get zeros above and below. Which one?
You can go with the first one.
What's that?
You can get the zeros below.
Zeros just below?
Yeah,
okay, then we'll do back substitution. Okay, that's fine. So what'll be the next thing we do then? That's we needed to decide then. Oh, Mohammed is here. Okay. All right. Okay. we're doing polynomial curve fitting, which is sort of long and tedious just because they're picking a large number of degrees here. But we started with five points. We're going to try to find a polynomial that fits those 5 points. It's going to have to be a 4th degree polynomial. Okay, always 1 degree less than the number of points you have. So that polynomial will be a sub 0 plus a1x plus a2x squared plus a3x cubed plus a4x squared. And then we take that and plug these values in. So the x's are your first coordinates and your y's are the second coordinate. So for the first one, the first p of -2 will be a0 plus or minus 2a1 plus 4a2, because you're squaring it, minus 8a3 plus 16a4, and that's equal to 3, y value. In that order fit.
Is that given or you just...
What's that?
Was that given or you have to...
Okay. This is the polynomial we're trying to fit these 5 points to. You know it's got to be a 4th degree polynomial. Okay? 1 degree less than the number of points you have. That's sort of the rule. If you think about it, if all you had was 1 point, a 0 degree polynomial will work. That's, you know, it's equal to 3. Okay? Yeah. If you have 2 points, what's going to fit that is a straight line, which is degree 1. 3 points will take a parabola to fit that, that's degree 2. 4 points, degree 3, and 5 points, degree 4. So that's what determines this. Now we plug in for x, the x values, and do what it says to, and this will become your y. I just moved it to the other side. So you don't have a, you see what's happening? Okay. So the second point will be a0, that stays the same. Minus 1 times a1, plus 1 times a2, minus 1 times a3, plus 1 times a4. And that's equal to 5. Okay. You put your first value in for your x's, second value in as a constant. Right? Third one is just a0 plus 0 plus 0 plus 0 plus 0 equal 1. So we know a0 is equal to 1. That's nice, because that we can, I'll show you what we did next. Okay? Next one is a0 plus a1 plus a2 plus a3 plus a4. You're just plugging in 1, and that's equal to 4. Right? And then the last one, plug in a 2 for your x, and you get a0 plus 2a1 plus 4a2 plus 8a3 plus 16a4, and that's equal to 10. So there's your 5 equations, 5 unknowns, but we can make life simpler by just plugging in a0 equal 1 here, 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 and here, because you know it's got to be. And then subtract that from both sides. Just subtract 1 from each of those. And that gives us our first row of the matrix, because you subtracted this over here. And that gives you minus 2 plus 4 minus 8 plus 16. This becomes a 2 now because you subtracted the 1 from it. The next one was minus 1, 1, minus 1, 1. 5 minus 1 is 4. Jump down to this one, 1, 1, 1, 1. 4 minus 1 is 3. Down here, 2, 4, 6, 8, 2, 2, 4, 8, 16, and then 10 minus 1 is 9. All right. Next thing we do, we wanted a 1 in the upper left. We got a minus 2. Notice that whole row is divisible by 2. So we just divided by minus 2. So row 1 divided by minus 2, and that gives you 1, minus 2, 3, minus 4, 1. Write down the rest of them. Okay? Then you wanted a 0 below this, so here we just added row 2 to row 1. Got that. here we subtracted row 1 from row 3, we got that. Here we did row 4 minus 2 row 1, and we got that.
And that third one, the one that's A0.
This one?
A0. So that one you just.
Oh yeah, you use that here, and so you reduced it, you lost one, you know this one already, okay? So use that and get it down to a 4 by 4. It's a 5 by 4, but, no, 4 by 5, but it's 4 unknowns, because you know this one, that's known now, okay? So incorporate that in the other side, because that's a known value, because of that statement right there.
So does that happen on every single situation? Or is this
Only if you have that. If you had a 0, 7, then this is A0 equals 7. But if you had a 14, 13, no, you got it. Yeah. You have to have a 0 there for this thing to work. And it doesn't have to be 1, it could be anything. But whatever it is, you can subtract it off and reduce your thing. Okay, now, before you came in, I was dealing with my consultant here, and he wanted to do Gauss elimination, not Gauss-Jordan elimination. The difference here is Gauss elimination, we just get zeros under the lead. Next thing we did, we wanted that to be a 1. It was a minus 1, so we just changed signs. So we had 0 plus, minus, plus, and then. I'm sorry. Once we had done this to it, this was 0, minus 1, 2, minus 3, 5. So we just changed signs, which is multiplied by minus 1. I didn't write it down, we just did it to get our 1 here. Now, if we're doing Gauss-Jordan elimination, we use this to make that a 0. But my consultant said, no, let's just do the ones below. We'll do back substitution later, but right now we'll just do Gauss elimination. So, the next thing is we want this to become a 0. Okay, so how do we make this 0 using that?
Multiply the top of the negative 3.
3 and add to the, yeah. So it'll be row 3 minus 3 row 2. All right, now I'm going to try to write it over here. I'm just going to have to cram it. Huh? Okay. What's that?
Oh, I see.
Okay. Now I could erase some other stuff. You want me to erase other stuff or cram it down here?
Usually I think you write the word would be multiplied by, and then you add it to the, that's what got me.
Yeah.
Because usually that's how you do it when you start it on the change. So you usually write row 3 times row 2 plus row 3.
Row 3.
Now you kind of flip it around, that's what got me confused.
Yeah. Okay. So you want to minus 3 row 2 plus row 3?
That's how you usually do it from my notes.
Oh, I see.
That's
Yeah. Well, I think he started telling me the other way, so I started doing it the way my consultant said. So it's his fault, you know.
This is it.
Yeah. Okay. Either way works. Yeah. Right. Okay. You want me to write it over here, or you want me to erase somewhere else? Because this is pretty cramped down here, but I can do it. Do it up at the top. Okay. So what I'll do, because we really don't need this anymore, and it should be the same size. Okay. All right, here's Daniel. All right. Okay. So we're not going to mess with row 1, so it stays 1, minus 2, 3, minus 4, 1. Okay. Now, I've already erased some things, Daniel, so I can't fill in all the blanks. But what we're doing is polynomial curve fitting. We have 5 points given, and it says find a polynomial that all 5 points fit. The smallest order that's guaranteed to work is a 4th order polynomial. Okay? It will have 5 parameters in it, because you have 5 points you're trying to fill. But one of these doesn't associate with an x, it's a constant, so you'll have 5. here's a polynomial, piece of x, so it's 5 points, fourth degree polynomial. A sub 0 plus a1x plus a2x squared plus a3x cubed plus a4x4. Fourth degree polynomial, 5 parameters, the a's. Okay? Then we take the x's and plug them in where x is, and then the polynomial value will be your y. So I'm going to move that to the other side. So this will be an a0 minus 2a1, plugging in minus 2 here, plus 4a2, you square minus 2 and you get plus 4. Cube minus 2 and you get minus 8a3, and then raise minus 2 to the fourth power, that's positive 16a4, and this polynomial then is equal to 3. When you plug in the x, you get the y. Your a's are your parameters, the unknowns here. You're plugging in x values and you're squaring, cubing, fourthing, whatever, and you're getting your y value. Okay? And you plug in a minus 1 for your x. A0 is still A0. And this will be a minus A1 plus, because you square minus 1, you get plus A2, minus A3, plus A4, and that's equal to 5. Okay? The next one, pretty nice. A0, that just comes down, plus 0, A1, A0, A2, A0, because when you plug in a 0 here, all those become zeros, and that's equal to 1. So A0 is equal to 1. We're going to come back to that in a moment. Okay? And then the next one is A0, and you plug in a 1 here, so it'll be 1A1 plus 1A2 plus 1A3 plus 1A4 is equal to 4. Okay? The next one, x equal 2, A0 plus 2A1 plus 4A2 plus 8A3 plus 16A4 is equal to 10. All right. The good news here, this one right here, A0 equal 1, no other parameters, you can plug that 1 into all those values and reduce it to 4 unknowns, not 5 unknowns, but 4, because you already figured out one of them. A0 is equal to 1. So that's what we did next. Well, I've already erased it. Our coefficients were minus 2, 4, minus 8, 16. When you subtract the 1 from 3, you got a 2. Okay? And then you did you subtract this, so you have a minus A1. I've already erased it. But it comes up just like this one. Minus A1 plus A2 minus A3 plus A4 is equal to, subtract the 1 from 5, you got 4. And then you went down to this one, 1A1 plus 1, 1, 1, 1, subtract 1 from 4, and you get 3. So A1 is. And then the last one was 2, 4, 8, 16, subtract 1 from 10, you get 9. So that's why the bottom one turned out the way it did. Now, how did this one get to be like that? Well, these were our coefficients, minus 2, 4, minus 8, and this wound up being a 2. We divided by minus 2. So this came up 1, minus 2, 4, minus 8, 1. No? Yeah, okay. But I've already erased it. You can't see it now. No. Did I do it right? I don't think I did. Because this should be 1, 2, minus 2. This should be a 4, not a 3. Whoops. Whoops, whoops, whoops. Huh? I've already gotten in too deep. I'm pretty sure that should have been a 4, and that should have been a minus 8, and then that would be a 1. And then I use this to do further on, so I really botched it. I messed up every one of these. Huh?
you're saying that
Because the first thing was that row 1 was divided by -2, and I just went down and did 1 minus 2. I made it a 3, and it wasn't a 3, it was a 4. And that would have been a -8. And then that would have been a 1. So I botched it up. This is all going wrong. Now, rather than go back and redo it all, but you see the general pattern that we have here. This is what you would have done if I had done it correctly. The book didn't do it anyway, so they wound up with A0 equal 1, which we did. And then I think I'm going to say thank you very much for me making a mistake, because the A1 turns out being a -30/24, which I don't know why they didn't write it as 15/12, which would have been 5/3. Why they left it, and then A2 was 101/24. A3 was 18/24, which is 3/4, and A4 was -17/24. That was your polynomial. We wouldn't have gotten it because I messed up that top row, and that messed up everything. But as it turned out, I'm glad I didn't have to do all those fractions. Okay, so sorry about making the mistake there. Thanks for coming in when you did, Daniel. That saved me from continuing. This would have been minus, ooh, my eraser didn't pick up. Okay. Okay. -2, 4, -8, 1. And I should have used that all the way through, so I'm not going to go back and do it, but you see the process, and you would wound up with, if we'd have kept going with the right numbers here, then we would have gotten 1 here, 1 here, 1 here, 1 here. That last one would have given us exactly what it was, which would have been a real big pain in the neck, because that last one was A4 would have been -17/24. And then we'd have had to backfill that here and here and here. You know, and every time we did, back substitute, and you would have gotten back. You actually saved me effort, because when I went to explain to you, I realized I messed up the first row. By messing that up, I messed up all 3 of these eliminations here. I'd have to redo all those. We don't have time for it. But if I'd have done it right, you will wind up with those coefficients. And weird coefficients, but they give a perfect curve fit for those points. -2, 3, -1, 5, 0, 1, 1, 4, 2, 10. And that curve, weird though it may be, does fit that. And don't expect life to be pretty. It will most often turn out bunches of weird numbers like that. All right. Example 3, sorry about messing up example 2, but at least I didn't waste huge amounts of time on it. Okay. Let's go to example 3. Find a polynomial that fits these points. 2006, 3, 2007, 5, 2008, 1, 2009, 4, and 2010, 10. Okay. Now, guess what, team? Do I want to do it? That's 1, 2, 3, 4, 5 points of the 4th degree polynomial. That'll be x to the 4th power. Do I want to raise 2006 to the 4th power? No, I don't. I don't even want to come close to that, okay? that would be absolutely miserable. Okay? So what they do, they translate and use a z which is a lot more reasonable. Okay? And that z that they use, my temptation would have been to use 6, 7, 8, 9, and 10. Just subtract 2,000 from those. But actually a better one would subtract 2006 from those, so you'd have 0, 1, 2, 3, and 4 as your lead term. But they do one even better than that. They take the middle value, 2008, subtract that from all those, you get a -2, -1, 0, 1, and 2, which will be...
They reserve what they subtract for later on, or it's just...
Okay, yeah, at the very end, you go back and add in the same thing you just took out. When you get your final answers, yeah, you just add that. Huh?
Let's do it and see.
Okay. So, first thing we're going to do is a substitution. And what they call this is a xy, x1, y1, x2, y2, x3, whatever it's that. And then they say z is equal to 2008. No, x minus 2008. So that then makes for your z1, y1, z2, y2, and on like this, that would be -2, 3, -1, 5, 0, 1, 1, 4, and 2, 10. Which, does that look at all familiar?
Yes.
That's the one we just did on the previous one, which I messed up. Okay? And they're just going to take the same coefficients they came up with, okay? And finally now, they, instead of z, they go back and put x minus 2008 in. And it makes for a big, ugly, hairy polynomial, but they leave it in that form. They still got it raised to the 4th power and 3rd power and 2nd power and stuff, but they just leave it in that form, which is fine. It seems like it's disingenuous, but it works. Okay? So they didn't want to go back and redo a 4x4, which we didn't do right the first time, and that messed up. So just showing you that's a technique to get your numbers smaller. Okay. Pretty clever to use the middle value, and then you have minuses and then plus, and it keeps all your numbers a little smaller. But you don't get around the fact that you still got a mess at the end. But you just eliminated a lot of pain in getting to the mess. Okay? Now here's another example of curve fitting. This is example 4. Okay? Find a polynomial that relates the periods of the 3 planets that are closest to the Sun to their mean distances from the Sun, as shown in the table. Then to test the accuracy of the fit by using polynomial to calculate the period of Mars, for instance. In the table, the mean distance is given in astronomical units, which is the distance from the Earth to the Sun. So that's why Earth is 1.00 in every case. Yes? Okay. Wait just a second. Let me turn this. All right. This was another application of curve fitting. It found a polynomial that relates the periods of 3 planets closest to the Sun to their mean distances from the Sun, as shown in the table. Then test the accuracy of the fit by doing the other. Distance is measured in astronomical units, which is the Earth distance.
The mean distance of an orbit is the semi-major axis, right?
Yeah. Yeah. Okay. Now, no, that would be the max distance, wouldn't it?
I think semi-major axis is the mean, and then semi-major max. Semi-major axis times the eccentricity gives you your apogee and perigee.
Okay. Alrighty. Okay. So what we have, I don't know. It's certainly doable, but whether we want to take the time to do it or not, I know what they're wanting to get to. I'd rather just go straight to that, but let's just go on and do this. So here's the planets here, okay, and this is, they go on across the top. I would have put them across the other. Mercury, Venus, Earth, and Mars. Okay. And their mean distance and their period. Okay. 0.387. As you can imagine, this is going to be a lot of fun because of the decimals. 0.723. 1.000 and 1.524. Okay. Periods 0.421, 241, 0.615, 1.00. Because not only is the period, they didn't say this, the periods are in Earth years. So that makes Earth 1 again. And 1.881. Okay. Now, 4 ordered pairs here. Your polynomial curve fitting would then be a third degree. So P of X would then be a sub 0 plus a sub 1 x plus a sub 2 x squared. Okay? My nose itches, I don't know why. So if you plug these in and they're letting the period depend on the distance, which is probably reasonable. Sorry. This would be XY pairs. This is your X, this is your Y. Okay? And you plot those points so your Y is the period at the bottom. Okay? So the first would be A0 plus 0.387 x plus, no, I'm sorry. Yeah, that, I'm sorry. 3.87A1. I always want to put the x being the variable. It's not. Okay. I think we're okay. Okay. 0.387 squared A2. Now, you can go on and multiply those out if you want to. Next one would be A0 plus 0.723 A1 plus 0.723 squared A2, because these are the distances you put in for, oh, I didn't put, equal to 0.241, and this one's equal to 0.615. Okay, that's the Y value at the end. And then The next one, Earth, is pretty simple. That would be A1 A0 plus A1 plus A2 is equal to 1. And then the last one would be A0 plus 1.524 A1 plus 1.524 squared A2 is equal to 1.881. So that would be your 4 equations for unknowns. Wait. Oh, I'm sorry. What they're saying do, I didn't read it carefully, use the first 3 to come up with the 3 variables, and then plug it in and see if it works for Mars. So that's what their deal was. No. Why are they doing it this way? Find the polynomial. 3 planets. Oh, I didn't read it. Find the polynomial that relates the periods of the 3 planets that are closest to the Sun, that's Mercury, Venus, and Earth, to their mean distances from the Sun, as shown in the table. Then, to test the accuracy, fit that to Mars and see if it works. Okay? So they aren't doing a 4 by 4, they're doing a 3 by 3. They're forgetting about Mars, they're going to use that one to check it. So forget this last one that I wrote down here. It would just be the...
So it would be completely impossible for the average distance to be more than 1 AU if the furthest object is 1 AU.
Yeah, no, but Mars is outside Earth.
Right, that's what I'm saying. So when you were saying before that it didn't work, that's what I was saying.
No. You'd have 4 equations with 3 of them.
Right.
See, what before they just estimated with a 3rd degree polynomial, but you had 4 points. So you needed, a 2nd degree polynomial, you'd need a 3rd degree polynomial. So why? Because they said do it with only the first 3, so it would give you a 2nd degree polynomial. Okay. So forget that last equation there. And that's doable. All you have to do is square these 2 numbers. They're ugly, but you can square them, and then do it. Now, it'll be a mess to do it manually. Use a computer. That will solve it. If any of you have graphing calculators, most of them have the capability of doing matrices. They're tedious to load, but once you get them loaded, they'll do the work for you. Okay? So rather than taking class time to row reduce those, they just show you the results. Okay? They just say, here's the approximate solution. And they come up with 3 values for the A0, A1, and A2. Okay, then they plug in Mars, the 1.524, it comes out 1.918, where it really should have been 1.881. Not a bad fit, but not on the money. Okay. And here's the reason. You were trying to fit this on a parabola. This is not a parabolic fit. Okay? What it is, and Kepler's 3rd law of planetary motion says that the square of that is proportional to the cube of that, or something like that. So they don't fit that way. How you make a better fit, because now that we know Kepler's laws, they don't even mention Kepler here, but because of his relationship, it's far better to use what they call a log transform. Okay? And what a log transform does is take it from being a polynomial fit down to being a... Good deal. Thank you. I guess since he showed up, I'll mark him, but not staying too long. Okay. Okay. You do a log transform, okay? So you take the log of each of these numbers, okay? And then you match the log of x with the log of y. You do your fit that way. And sorry, I got something in my throat. I really don't care for this at all, because here's how he expresses it. Now, fitting a polynomial to logarithms of distances and periods produces a linear relationship. Okay, that comes from Kepler's third law, but there's no other reason to have assumed that. And he doesn't even show you how you do that, okay? He just says it's this, and this is what it comes out being. And then they show you the graph, and again, these graphs are awfully close. Okay? By the polynomial fitting, you see these go right through because you fit them to it. When you plugged in Mars, I don't know if you can tell from where you're sitting, Mars is just a little bit too far this way. Okay? Actually, said another way. Mars is there, but it predicts it to be a little bit higher. Okay? 1.99 something, or this is 1.88. So it's not quite a great fit, but when you do the log transform, which you need to do here because it wasn't parabolic in the beginning, because they relate by cubes and squares, that a log transform makes that 3 halves. The coefficient is 3 halves. You could do the multiply by 2 over here, that'd be log of y squared, or log of y squared is equal to log of x cubed, and take the e to both sides, and you have y squared is proportional to x cubed. And sure enough, that is a great fit. And as you see there, the line seems to pass smack dab through all 3 of them, all 4 of them. I'm sure there's some variation, but not nearly as much as before. What's even more so, go and plug Jupiter, Saturn, Uranus, and Neptune in with their enormously bigger numbers than these, and they still fit almost perfectly. Okay, so that's why Kepler's third law works, because it's a great fit. It would not even come close to a parabolic fit. Because Mars was a little off, the rest of them would have been way, way, way off. So, without showing you anything, he's just saying this stuff. Okay? Now, if you go down a little further, linear algebra applied, researchers in Italy have been studying acoustic noise level from vehicular traffic at busy 3-way intersection on the college campus, used a system of linear operators. So they give you some a source here. If you wanted to write on there, there's a potential paper topic. Sounds a little deep, but you might find it interesting. Okay. Another use of application of linear equations are network analyses. Okay? And again, they don't go into great detail here, but I'll give you what they got. Okay? Here is an example. You got input coming this way into what I call a node. I don't know what they call it. Junction. Okay. And then you have output coming out of that. Okay? And if you knew this was 25 coming in, but you don't know the output, they could be x and y. But if you know the directions are being shown as indicated here, then you know that x plus y is equal to 25. Right? Because the input has equal to outflow. You don't have a source or a sink there at the junction. you have distribution. Okay. Now, that's background. Let's actually do a network here. We have 5 junctions. 1, 2, 3, 4, and 5. Okay? And we have links from every one to every other one that you can get to. 1 and 5 don't have a direct link, but the others do. Okay? Oops. All right. So you have 2 going to 1. You know you have 20 going that direction. 3 going to 4. You know you have 10 going in that direction. 3 going to 5. You have 10 going in that direction. Okay. That's all you're given. Now, they assume x1 going to x4, from 1 to 4 is going to be your x1 in that direction. Now, they may be wrong on that. They may have it wrong. Okay? x2, they're assuming goes this way. x3, they're assuming goes this way. And x4, they assume is going up this way. I'm not sure why. And x5, they're assuming is going that way. Okay. Now, you've measured the top and 2 of the angles at the bottom. The rest of them are you're trying to determine. I guess all these sort of make some sense. The thing to me that makes the least sense is it seems like you got, no, it's okay. Okay. But just understand, any one of these could be pointing in the wrong direction. But then what you're going to have is a negative. Now the 20 and the 2 10s, they have to be pointing, you know those, so they're going correctly. So what do we do here? We add the things that we know. Let's take junction 1 at the junction. At junction 1, we know that 20 is coming in and x1 and x2 are going out, so you know x1 plus x2 is equal to 20. Any doubt about that? Here's 1. You got x1 leaving, x2 leaving, 20 coming in. Those 2 must add to be 20. Now, if one of these is direction wrong, you're just going to come up with a negative, and it'll still be okay. Okay. You take junction 2. What could you write about junction 2? Here's junction 2. What can you tell me about it?
X4 is going up.
Okay. That's coming in, so x4 is a positive. And the minus x3 plus x4, that equals 20, right? Because what's going out plus in is what's going out. Okay? So x3 and 20 are going in the same direction. So, and you notice they're on opposite sides of the equal sign. So in other words, x4 is equal to 20 plus x3, right? You've just written them on the other side. Okay? How about junction 3? What can you tell me there? x2. Second. Going in. Plus x3 was going in. And again, you have the outflow, 10 plus 10 is 20, right? So that's what's going out. Right? Okay. How about junction 4? Okay. So you want that to be a minus X5? Okay. So X1 minus X5. Now this one has to be minus 10 because we've had on the other side what's going out. So in other words, X1 plus 10 has to equal X5, right? X1 plus X plus 10 equals X5. That's going out, right? So you move the X5 over here, but you have to move the 10 over there. Is that right? Right. So that's junction 4. How about junction 5? Say that again. X5 is going in. Is that what you said, or 10? At 5? This is a 5 down there. 3's right there. Okay, X4, so minus X4. Minus or plus? Plus X5. Now, X5 and 10 are the same signs on the same side, so again, that's going to be a minus 10. So I would have been tempted to make this a plus, this a minus, and that a plus. I mean, just because I like pluses better than minuses, and you got 2 to 1. So it doesn't matter. That's perfectly fine too. But if you have this coming in is the positive, so going out would be, on the other side would be positive, X4 minus X5. It says the same thing, it just leads with a minus. It doesn't matter. I just really didn't care much for that. It doesn't matter, both of those are fine. Let's do the matrix. What would the matrix be? 1, 1, 0, 0, 0, 20. Next. Okay. Just for fun, I want to swap these 2 rows. Can I go on and do that? Okay. 0. 1. I want to swap those 2. 1. 1. 20. Right? Okay. And then we'll do the third one. It was the second one. 0, 0, minus 1. 1, 0, 20. Then 1, 0, 0, 0, negative 1, negative 10, and 0, 0, 0, 1 minus 1, 10. Okay. Perfectly fine. Now I wish I had changed the sign of this one so we have 1 there already. But it's okay. It'll work out. All right. Now, fortunately, you got a lot of zeros in it already. So what you want to do? Should I check with my consultant, or do we just go? Okay, you got 1 where you want it, and you have, this is the only thing you need to change here. So let's do that. Okay. So that will be, how do we get this to change? Minus row 1 plus row 4. Okay. Going back to the way you like to see them. Okay. Now at the same time, I want to change signs minus row 3. I want to just change those signs so that becomes a plus 1. Is that okay too? All right, so the top row stays the same, 1, 1. 0, 0, 0, 20. 0, 1, 1, 0, 0, 20. And then negating row 3, that'd be a 0, 0, 1, minus 1, 0, 20. Minus 20. I negated it. That's going to be hard to see, so let me make it easier to see. I negated the third row. Okay? Now we do the fourth row. I think of row 4 minus row 1 is 0. Next. Row 4 minus row 1. Minus 1. Next. That's a 0. 0. Negative 1. Negative 30. It's not looking too good, is it? Okay. Now the last, that's a 0, so we just write that down. 0, 0, 0, 1 minus 1, 10. Okay. All right. So, what you want to happen? You want a 1 here, 0 is below it, you got it. Next, you want a 1 there, and 0 is below it. Now, my question to you, you want Gauss-Jordan or just Gauss? Gauss, okay. So what do we do to make that become a 0? Add those two rows. Row 2 plus row 4. So, what's that? We're over time. Okay. Let's stop then. And I'll let you finish this one. It's not hard. The math in it is not difficult. But see what you can get. Continue with that one. And we'll pick up Kirchhoff's laws for next time. I had hoped we'd finish this section, but this is just too long. We almost finished. We'll finish next time. Homework exercises, you can do as many as you'd want of 1 through 11. Frankly, I doubt if you'll do too many. I think I'd stick with the 3s, so that gives you all quadratics, but you might want to go for one bigger if you want to. Then do any of the odds 13 through, goodness gracious, I'd say either 13 or 15. Then try 17, 19, that's one more like the one that you have to do adjusting. 21 is a guided proof only if you want to do that. 23, well, hold off there. No, 23 I think you could do, and possibly 25. Network analysis, if you are successful in this, you might want to try 27 and or 29. And we'll stop there. Pick up the rest of it. Good deal.
Okay.
Sorry we went over.
Yeah, I forgot that we lost some time.